Okay, so welcome back to another video. So here we have an improper integral from 0 to infinity of the natural log of e to the x plus 1 divided by e to the x subtract 1. So yet we have another natural log slash exponential function hybrid integrand. So one might think that we can actually use natural log properties, that we can actually split this so that we can actually use, it's a difference of two improper integrals. Well, the idea of using properties of the natural logs will come in handy, but that's not the first step we're going to take. We're actually going to get a little bit creative in a sense that we're going to manipulate our integrand first in order to make things a little bit easier, and you'll see where I'm coming from with this. Expect some use substitutions. There's actually going to be two functions we'll be using further along into the procedure. So that's some special functions specifically, and that's just nothing really much that needs to be said there, because it's, just generally how most of the integrals that I've calculated in videos, it's direct computation from there. So other than that, let's actually just jump right in. We'll start by getting a little creative, and we'll multiply e to the negative x to both the numerator and denominator of our natural log argument. Let me call this capital I first. And so far we'll have that this is 0 to infinity, and this is the natural log of, so this is after applying that multiplication, we'll get 1 plus e to the negative x, and then divided by 1 minus e to the negative x, then dx. Now from here, let's actually apply some u sub. So this makes things a little bit easier, hence the manipulation. You'll see where we're going from with this. You can actually do the u sub from here if you want to without having to perform all this, but personally I think this is actually it helps a little better. So we're going to let u equals e to the negative x, then standard differentiation for both sides. We have that this is negative e to the negative x dx, but we just have a dx to substitute and nothing multiplied with the negative e to the negative x. So let's actually just divide this to both sides and replace that with the u, and so we get that negative du is negative du divided by u is equal to dx. And let's actually calculate the bound. So we plug this in. So for x equals infinity, that means u is going to approach 0, and then if we let x equals 0, then that means u is going to approach 1. So let's put all this back together, and so we have that now our new integrand in the world of u is going to be the bounds from 0 to 1, for 1 to 0, 1 being the lower bound, 0 being the upper bound, of the natural log of 1 plus u, and then we divide this by 1 subtract u, and then replace this with our dx differential. So this is negative du divided by u. We can fix this up a little better. For one, we can have to switch the bounds of integration. That becomes negative, and then that negative will cancel out. And I'm going to move the 1 over u to the front of the natural log as well. So this is going to become our new integral from 0 to 1 of 1 divided by u multiplied by the natural log of 1 plus u, and then divided by 1 subtract u, then du. And as I said, we will be using some natural log properties to make things a little bit easier, especially now that we have a division of the input. So applying that, so we're going to use some linearity, of course, and then this comes out to the following integrands, or a new simplification for I. We're going to get that this is from 0 to 1, and then first we have this is the natural log of 1 plus u divided by u, then du. Then we can subtract this with the same thing, except now the input for the natural log is going to be 1 subtract u, and then divided by u, then multiplied by du. So what do we do from here? How can we proceed forward from here? This seems like an integrand like this is difficult to use elementary calculus in order to get some sort of elementary antiderivative out of that. Well, we're actually going to be using the Maclaurin series of these following functions over here. And so I'm going to write down what those Maclaurin series is going to converge to specifically for these numerators. So for one, we have the Maclaurin series for the following functions over here. So for one, we have first the natural log of 1 plus u is going to equal to the following infinite sum. So we have the infinite sum n is equal to 1 of negative 1 to the power n plus 1, then multiplied with u to the power n divided by u, and that is for u is in the specific interval from negative 1 non-inclusive and then positive 1 inclusive. So that's one that narrows it down. So let's actually use the second one. And so the second Maclaurin series we'll be using is the natural log of 1 subtract u. What that's going to converge to is the following infinite sum. This is going to be negative, then multiplied with the infinite sum, n is equal to 1 of u to the power n, then divided by n. And of course, this is for u is in the interval -1 inclusive, and then -1 not, and then +1 non-inclusive. So with these two functions over here, or the two Maclaurin series of those natural log functions, we can now actually do the substitution back here. Putting all this back in, so we have that capital I is going to equal to the following. So we have the integral from 0 to 1 of 1 over u, then multiplied with the infinite sum. So just plug this back in. So this is -1 to the n plus 1, and then u to the power n, and then divided by n, then du. And then we're going to add this over here with the integral from 0 to 1 of 1 divided by u, then multiply with the infinite sum, n is equal 1 of u to the power n, and then divided by n du. We're basically just doing the substitution. And of course that's a negative, since we have a minus, then distribute that minus, that becomes a plus. With all this, now let's actually now interchange the sum and the integral. So the infinite sum comes outside. So n is equal 1 of -1. So everything stays in for the u inside the integral, and divided by n. Multiply with the integral from 0 to 1 of u, and then n subtract 1. Since I just rewrote this from the u, put this back here. Du, add this again, so interchange the sum outside with the integral, so infinite sum, then what do we have? So this is 1 divided by n, and then the integral from 0 to 1 of, again, u to the power n subtract 1, and then multiply with du. I think it's self-explanatory to see that the antiderivative of the integral 0 to 1 of u to the n minus 1 du, that's basically just equal to u to the n divided by n. From 0 to 1, just plug this back in, we see that this is just 1 divided by n. And so with that, we can actually just substitute the 1 over n for these definite integrals. Putting this back in, so now we have the infinite sum from n is equal 1. So we have -1 to the power n plus 1, and then divided by n squared. Then add this with the infinite sum from n is equal to 1 of 1 divided by n squared. So this infinite sum actually looks very familiar to a lot of the viewers here. Well, especially if you know what the function is, even if you don't watch my videos, but you know where I'm coming from with this. So this value is actually the Riemann zeta function, aka if you evaluate this at n is equal to 2, so that, let me first write that Riemann zeta function. So we have that this is actually the integral, or the infinite sum, of 1 divided by n to the power s. Put this like so. Then if I put this for 2, so that means the Riemann zeta of 2 is just infinite sum, n is equal 1 of 1 divided by n squared, which actually that converges to pi squared divided by 6, aka that's known as Basil's problem, so we can actually fill this gap in later. But then there's also one thing left. We have to figure out what this sum converges to. So this actually is known as the Dirichlet eta function, and so that actually comes down to the following infinite sum. So this is going to equal to the infinite sum from n is equal 1 of -1 to the power n plus 1, and then divided by n to the power s. And so that basically says that the Dirichlet eta, or eta of 2, and that says that Dirichlet eta of 2 is just equal to this following over here. N is equal 1, -1 to the power n plus 1, and then divided by n squared. But it has to come to some finite value, which it does. What we can do is we can actually use the relationship of the functional equation of Dirichlet eta in respect with the Riemann zeta function. And what that comes down to is, put this line over here. So the Riemann zeta, or the eta of s, is going to equal to 1 subtract 2 to the power 1 subtract s, then multiplied by the Riemann zeta of s. And we just plug 2 back here. This is just going to be 1 subtract 2 to the power 1 subtract 2, and then multiply with Riemann zeta 2. Then this actually just goes to, it's 1 minus 1/2, and then that's just 1/2 multiply Riemann zeta of 2. We know that Riemann zeta 2 is just Basil's problem, so put this back in for pi squared divided by 6. And so what that gives us is actually just pi squared divided by 12. And so therefore, capital I, which is our given integral that we want to solve for, is basically just replace this with pi squared divided by 12, add this with pi squared divided by 6, and then if you just reduce the fraction out, we're going to get that the final answer of I is going to equal to pi squared divided by 4. And so just like that, that completes the evaluation of the natural log of e to the power x plus 1 divided by e to the x subtract 1, the proper integral of both the natural log and exponential hybrid integrand. So yeah, that's pretty cool if you ask me.